In this video, we'll look at how carbon dioxide affects stomatal pore size, stomatal opening. We'll look at how HT1 is involved in the process and how Ca is involved in the process. And then we'll use this video as a way to carry out a double mutant analysis to figure out which comes first, which comes last in the ordering of these proteins' activities. Okay, so in order to look at the role of carbon dioxide on stomatal opening, we have to measure stomatal opening. And the way it's done, apparently in this experiment, is to measure stomatal conductance, how much water is leaving the plant at a given time. Now, since this is pore size, that could have also been given as some sort of dimension, and this could have also been called stomatal opening. Okay, so the wild type plants are the white bars in each of these three different environmental conditions. Here's 100, parts per million carbon dioxide. Here's 400 parts per million carbon dioxide. Here's 800 parts per million carbon dioxide. Wild type seems to have pore size or stomatal conductance most open when carbon dioxide are lowest. This is your standard current concentrations of carbon dioxide, and these are elevated concentrations of carbon dioxide. So it looks to me as though the higher the carbon dioxide, the less open the stomata are. Now, let's look first, since we've done it before, at HT1-2. So HT1-2 is a loss of function mutant allele. Okay, so if you see a bar for what HT1-2 plants are doing, you know that's what plants do in the absence of the HT1 protein. Okay, so it looks to me as though there's a very reduced opening in all cases, all environmental cases, when HT1-2 is the allele, so no HT1. So if no HT1 leads to closed stomata, then HT1 must open stomata. Now let's look at this Ca protein. Now this Ca minus is a mutant in which the Ca protein is missing. So again, it's a loss of function mutation. Okay, no Ca protein activity. When there's no Ca protein activity, here's the three different environmental conditions. In all environmental conditions, all CO2 levels, the plants without Ca have wide open stomata. So then, if that's true, when they're missing, the stomata are wide open all the time. When they're present, what do? I look at what the wild type is, because the wild type means that's what's the situation when all of the proteins are present. Wild type, at high carbon dioxide levels, you have relatively closed stomata, as compared to the mutants, where you're still got very wide open stomata. So it stands to reason then that when Ca is missing, the stomata stay open. Ca is involved in the closure of stomata. Okay. Now I'm going to show you that you can order the pathway. There's two different possibilities for ordering the pathway. So we said, I'm going to write this over on the side, HT1 opens stomata, and we said CA, when active, closes stomata. Okay, so then if I draw this pathway in the two possible ways it might work, either, let's say, HT1 regulates CA, which leads to either the opening or the closure of stomata. And just say, for this one, it's closure. That'll make it easier to figure out. Okay. Whereas if it's the other way around, we have to order it in this way. CA comes before HT1, regulates HT1, and HT1 leads to opening or closing of stomata. But since we know it opens stomata, I'm going to write it like that. So these are the two possibilities. So let's look at this one first. Let's look at possibility 1 first. If CA's relationship to closure is that it closes, so I get to draw an arrowhead. If it prevented closure, I would have to draw a blocking arrow, as they're called. That's an inhibition, and this is activation. Okay, so if this is the pathway, CA has to lead to the closure of stomata, and what will HT1's job be? Well, HT1 opens stomata, which means you have to prevent the closure of stomata. So that would be an inhibitory arrow. So HT1 blocks CA, therefore CA fails to close, and they stay open. Okay, makes sense. All right, now what about in this case? HT1, we've already figured out that it opens stomata, so I get to, again, draw this line. If HT1 opens stomata, and CA is involved in the closure of stomata, then CA, if it comes and regulates HT1, has to shut it off. Okay, if you stop AT1 from opening the stomata are closed, and that's what CA does. Okay, so both of these, option 1 and option 2, are possibilities. But what's the reality? Well, I'm going to show you the double mutant data. So at very low carbon dioxide concentrations, that's what you see. At current level carbon dioxide concentrations, you see the same. At high levels of carbon dioxide, you still see the same amount of stomatal opening. So that's the double mutant phenotype. Okay, now let's look and see if this works, if this pathway works given the double mutant data. What would the result be if I get rid of this gene, if I block out, if the mutation is in the CA gene, so there's no CA. Well, with no CA, there's no closure, and so you're going to have open stomata. And HT1 is got nothing to regulate, so the double mutant phenotype is going to be open stomata. It isn't, is it? We've just eliminated the possibility that that is the regulatory pathway for stomatal opening and closure in response to carbon dioxide. Now let's look at this pathway. HT1 opens stomata. What happens if HT1 is broken? If you lose HT1, what is your phenotype? Well, you don't have open stomata, you have closed stomata. And it doesn't matter that CA is wrecked. It's wrecked. We know that it's supposed to regulate HT1 in this way. HT1 isn't present, so the double mutant phenotype and this mutant phenotype would be the same, which would be always closed. And that is what we see. That is the result we see in these double mutant data. So if this is the pathway, Ca blocks HT1, which opens stomata. What's the relationship of carbon dioxide level to that pathway? Okay, when carbon dioxide levels get high, in a wild type plant, remember, stomata close. Okay, so you can't have this happening. So you want closure. So you want to activate Ca. When Ca is active, that's when you don't get opening, so you get closure. And so CO2 has got to activate Ca, which is going to shut down HT1, preventing the opening. Whereas if the carbon dioxide is low, well, then carbonic anhydrase isn't activated, and then you don't shut down HT1, and so then you do open the stomata. So this is the regulatory pathway from carbon dioxide level to the opening or closure of stomata. A stands for carbonic anhydrase. Carbonic anhydrase is involved in the process of C4 photosynthesis. It's actually taking water and carbon dioxide, generating. Also, it works in the opposite direction, as we'll see later in the class. And then you're ending up with protons and bicarbonate ions. Does that make sense? Well, there's 3 oxygens, there's 3 oxygens, there's 2 hydrogens, there's 2 hydrogens, and there's 1 carbon, there's 1 carbon. Good. All makes sense. That is the enzyme, carbonic anhydrase, that catalyzes this process. So, carbonic anhydrase makes this, and apparently this is what regulates HT1. Ta-da!